just a reminder of where we're at. Our idea is that we're going to take a differential equation, take the Laplace transform of both sides. This gives us an algebra problem to solve. And we're able to solve for y of s, which is the Laplace transform of y of t. Okay, now what we're going to talk about in this last section is that you can undo the Laplace transform using what's called the inverse Laplace transform, which is just going to go back to the t land. And so the basic idea is that if the Laplace transform of a function little f of t is equal to big F of s, then the inverse Laplace transform of big F of s is basically a little f of t. They'll be equal for our purposes. This inverse Laplace transform is a linear function, just like the forward version, the Laplace transform was. Okay, so if we had the inverse Laplace transform of a sum, we can break it up across the sum. If you had scalar multiples, we can pull the scalars out. And so this makes it very convenient for working with sums. Okay, so below here is a list of some common transforms. So for example, if we wanted to know the inverse Laplace transform of 1 over s plus 3 over s plus 2, we could use this linearity to say, I'm going to break this up as a sum, 1 over s plus inverse Laplace transform of 3 over s plus 2. Okay, 1 over s we see in our list, that's going to be equal to 1. The 3 over s plus 2, we don't quite see that. We see this number 10, 1 over s minus a, but we can use linearity that 3 can be pulled out front. And so this is 1 over s minus negative 2. And so we're left with 1 plus 3 e to the negative 2t. So this gives us a way to go back from the Laplace transform of our solution to our actual solution. Okay. The one, so this is not a complete list here. There's a bigger list in the formula sheet that you'll be able to use on your exam. One caveat is that just like in this last example where we had to like move things around a little bit, like the 3 outside of the inverse Laplace transform, we often are going to need to like massage the functions, especially the coefficients, a little bit to put them into the correct form. And so when we're trying to decide like what rule to be using, you want to keep in mind that the coefficients, these scalars multiplying our expression, can often be changed, but the s and its powers really can't be changed so much, and so you want to make your decisions based off of s and its powers. Okay, and we'll figure out how to make the coefficients right. So as an example of that, if we take a look at this next one, the inverse Laplace transform of 1 over s squared plus 4, I'd like you to take a look through these options, say what reminds you of 1 over s squared plus 4. And I hope you were thinking along the lines of either this s over s squared plus k squared, or k over s squared plus k squared. The first thing you want to focus on here is that you see this s squared plus a constant. So here our k squared is going to be equal to 4. So k is 2. And then next, so that narrows us down to either 12 or 13. And then next, what I'd like you to think of is what you see in the numerator. So in our term, we just have a constant in the numerator. In the cosine term, there's an s up top. In the sine term, there's just a constant. Okay. So indeed, we're going to be trying to match this sine term because it doesn't have the s's in the numerator. So we're going to be using that the inverse Laplace transform of 2 over s squared plus 4 is equal to sine of 2t. That's not quite what we have, right? We're missing this 2 up top. So I'm going to divide by 2 outside and multiply by 2 inside. Okay. So linearity says that these coefficients can be moved in or out of the inverse Laplace transform, no problem. Okay. We haven't changed the value because we multiplied by 2 and divided by 2. But now we match up the format that we're trying to agree with. All right, next let's take a look at this inverse Laplace transform of 2 over s to the 5th. Okay, take a moment and look over these different pieces and see which one do you think looks most likely. Okay, so here again, we're going to be focusing on powers of s. So here we see a power of 5, which is bigger than we see anywhere else other than in this t to the n expression. So here, based off of the format of this looks like n plus 1 is equal to 5. So we're just matching the power of the s first. So we're going to match powers of s first. So that tells us that n equals 4. Okay. And so the formula that we'd like to use is that the inverse Laplace transform of 4 factorial over s to the 5th is going to be equal to t to the 4th. Okay, so you'll notice that we don't quite match this 4 factorial. Remember that 4 factorial means 4 times 3 times 2 times 1. So we're missing 12 up top. So all we're going to do is multiply in and divide by 12. So this is going to be 1/12. Inverse Laplace transform of, and instead of writing, well, let's write it as 4 times 3 times 2 over s to the 5th. So this is 1/12 inverse Laplace transform of 4 factorial over s to the 5th. So this guy is 1/12 inverse Laplace transform of 4 factorial over s to the 5th was equal to t to the 4th. Okay. Oops. Just realized we hadn't circled our answers. Here we go. All right. So match the powers first, find out what any constants are equal to, and then adjust the coefficients as needed. Okay. We're going to do just a couple more examples.